Hey everybody. Sorry I'm a little late getting this video posted, but it should be up before the start of school tomorrow. But I wanted to go ahead and do a recording about lesson 701, which is projectile motion. Hopefully this is helpful for you. And I do have a video that I've included with this PowerPoint, but I'll upload that in the announcements like I did with yesterday's announcement. So we're going to start with the history of projectile weapons. Weapons have been used throughout history to launch objects or projectiles. The Romans used catapults, which are pictured here on the board. And in the Middle Ages and in the early Renaissance period, oops, I skipped through, but anyways, they started to replace catapults with cannons and gunpowder. So one of the key terms that we're going to need to be knowing as we talk about projectile motion throughout this unit is this term of trajectory. Hopefully it's a term that you've all been familiar with before, that you've heard before. Is a very common word in our vocabulary, and this is simply the path of a projectile. And if you're thinking about a projectile, you should always think that the path is going to be curved. It's not going to be that straight line of motion like we have been studying so far. So just to refresh our memory, remember that Galileo studied the properties of motion, and he concluded that objects fall at the same rate regardless of mass. So that's where we get that acceleration due to gravity. An object at rest will remain at rest. And if the object is moving at a constant velocity, it's going to be staying in a straight line unless an outside force is acting on it. So this probably, hopefully, sounds really familiar because it's basically Newton's first law. So Galileo's findings on inertia were restated by Newton. And then also Galileo found that objects in free fall can be described by the kinematic equations that are on the board. These wonderful equations that we've been using for the last unit, working on resolving vectors and net forces. We're going to continue to build on that as we work through projectile motion. So there's different components of motion, and Galileo discovered that motion, even in a straight line, has a horizontal and a vertical component. So as this picture shows on the board, we have this ball that's rolling on the table and then falls. And you'll notice that it doesn't fall like straight down to the ground. It has a minute difference in the distance that it's traveling horizontally as it falls vertically. And that gives sort of like that curved path that we're going to really be studying while we talk about projectile motion. So why do projectiles follow a curved path? This is where that video is going to come in. When we talked about Newton's laws of motion, I had some football videos. This video goes along with that, trying to relate something that we pretty much all are familiar with to physics. And it's going to be talking about when a football player punts the ball or they're kicking a field goal. It has that curved path as the football player kicks the ball. And that's really another form of projectile motion. So that video, I'll include the link when I post this recording in the announcements. I encourage you to watch it to try to get a better understanding and try to relate it to something that you would have seen in everyday life. So what does this mean mathematically? As we saw when we were resolving vectors, moving objects had both a horizontal and a vertical direction. So remember, the horizontal was the cosine of an angle, and then the vertical was the sine of an angle. We can apply these same equations to a horizontally moving object where t equals 0 degrees. So then you have the following equations. which we've already talked about. So horizontal distance, the little chart over to the right, these are some of the formulas that we'll be using throughout this lesson. So it's really important that you take a snip of this or you write them down. But the horizontal distance that the object moves is x equals vx, which is the velocity of x, times time. And then the vertical distance, or the altitude, is going to be y equals 1/2 g, where g equals gravity, times time squared. And then the other formula that we'll be using throughout this lesson in particular is t equals the square root of 2y divided by g. And all of these equations are going to assume no air resistance, which is the problems that we work through in this lesson are going to assume no air resistance, because if we assumed air resistance, we would have to add in another force. So let's start right off with our first equation. I'm going to go through these. I've put the steps here, and then I've worked through the problem in the following slides. I would encourage you to pause as I go through these while you're watching the recording, so that you really can stop and look at them and see what's happening in each step. But a boy throws a stone horizontally with a velocity of plus 20 meters per second from the top of a cliff that is 44 meters high. How long does it take the stone to reach the ground? What will the range of the stone be? So these are the steps that we're going to work through. We're going to always list what is given and what we're looking for. We're going to say what equations are going to help us relate the given and the unknown quantities. We want to make sure the equations are in the right form so that we're solving them correctly. And then we're going to calculate the time it takes the rock to drop to the ground. And then when we know the drop time, we can calculate the range. So step one, what is given? We're given our velocity x, our plus 20 meters per second. We know what our initial acceleration x is. So in the horizontal, it's going to be 0 meters per second squared. We know that our drop, the acceleration for y, is going to be gravity because it's dropping from a cliff. So it's going to be dropping towards the ground. So that's going to be plus 9.8 meters per second squared. And then we know our y, our total altitude, is 44 meters. So we're looking for time and we're looking for the range of x. So what equations are going to relate the given information and the unknown quantities? We're going to have horizontal distance equals that x vxt. That this x between the v and the t should have been subscripted. And then we know that our drop time is t equals the square root of 2y divided by g. So when we look at these equations, are they in the right form for what we're trying to find? Yes, thankfully we don't have to rearrange equations. So first we're going to calculate the time. So we're going to take that time equation, t equals the square root of 2y divided by g. We're going to plug in our numbers. Y is negative 44 and g is negative 9.8. Remember, it's dropping horizontally. It's dropping, so it's going to be negative numbers. And then when you do all that math, it boils down to t equals 3.0 seconds. So once we have that time, we now can put that information into our range, our horizontal distance equation, which is x equals vxt. So that math is going to be plus 20 meters per second because our velocity is still that plus 20 meters per second times that 3-second time. And when we do that math, it's going to give us plus 60 meters. So that's how far the stone's going to go. That's the range. The horizontal range is plus 60 meters. The time that it takes for the stone to reach the ground, that is our 3 seconds. So we also, because we're talking about a projectile, they're going to have an angle to them. And it's a good thing that we're really good at vectors now, because for any projectile, the velocity is a vector. and can be broken down into horizontal and vertical components, just like we've been doing all along with our resolving our vectors and our net forces. For a projectile that's launched at an angle, if your angle is greater than 45 degrees, the vertical component of the velocity is going to be greater than the horizontal. And if it's less than 45 degrees, the opposite is true. The vertical velocity is going to be less than the horizontal. And so these are the equations that we will be on the right-hand side of the screen where you see the picture. These are the equations that we'll be using to solve problems of an angled projectile. So your horizontal distance, your range, it's going to stay the same. It's still going to be x equals vx times time. Your vertical distance is going to be y equals vyt, so velocity in the y direction times time, plus the 1/2 times gravity times time squared. And then your total time is going to be negative 2vy divided by gravity. So I suggest you take a snip or write those equations down as you work through the problems in this lesson. There are some characteristics of angled projectiles, and they're all laid out with words as well as with a picture here. So you have your start position, which is 0, 0. So if we were looking at a coordinate graph, that's where your start position would be. Your upward path is your horizontal velocity is constant while gravity pulls on the projectile. Then you'll have a maximum altitude, which occurs at half of the time because of the parabola, which is what this projectile looks like, is symmetrical. And then you'll have a downward path where your horizontal velocity is constant and gravity is pulling on the projectile in the direction of the vertical motion. And then your end is where your horizontal velocity is constant and your vertical velocity is the same as it was at the start. And we have one last problem for me to work through in 2.5 minutes before I run out of time on this recording. So if I'm going to upload the presentation as well, so if you need to go back and look at it, you can. A boy throws a stone with a velocity of plus 20.0 meters per second and an angle of 30 degrees. How long does it take the stone to hit the ground? How far will the stone have traveled when it hits the ground? How high will it go? So step 1 is what is given and what are you looking for? That's always our step 1. We're given our velocity at plus 20.0 meters per second. We're given our angle of 30 degrees. We know gravity is negative 9.8 meters per second. And our unknown is the time, the range, and the altitude. So here are our formulas that were on our previous page. These are the formulas that we'll be using to figure out this problem. The equations are in the right form, which is great. So first we need to find Vx and Vy, and that's where we're going to go back to that vector solving that we've been doing previously, and that's where Vx will equal V cosine of the angle. If you work through that, you get plus 17 meters per second, and our Vy is going to be V sine of the angle. And if you work through that and you put it in proper scientific notation, you'll get 1.0 times 10 to the first degree meters per second. Next, we need to calculate our time. So here's our time formula and working through that one. Then we need to calculate our horizontal range, which is the same formula that we used previously. And the steps are there. And then you can calculate the maximum altitude. And there are the problems for that. Okay, so that is the end. I'm sorry I had to rush through that last problem, but I only have a limited amount of time that I can record. Hopefully that's helpful, and I will see you guys next week.